What are the properties of cathode ray? आपके एग्जाम्स कब है नेहा? 23rd?
Yeah, chemistry is on 23rd.
Okay, and from this chapter, what are the topics? Whole chapter is coming,
From
or
this,
there are some topics?
from the second chapter, it's the first half is cut for us. It starts from Bohr's postulates.
Okay, till Bohr's postulates.
Yeah,
Fine.
from there till the end of the chapter.
Okay, okay. From Bohr's postulate to the end of the chapter, it's coming, right?
Yes, ma'am.
Okay, no problem. We will cover that. If possible, we will take extra class also. Okay, so see the properties of cathode ray. What are the properties? So according to the experiment, the scientists draw some properties. So he observed that cathode ray travel in a straight line, right? Cathode ray travel in a straight line, like you can see over here. Yeah, this was the experiment, right? So here, J.J. Thomson saw that cathode ray is traveling in a straight line in the absence of, yeah, in the absence of electrical and magnetic field, right? But if you apply some electrical or magnetic field, there you will observe some deflection. Okay. Second property was that cathode rays produce mechanical effect as they can rotate the wheel placed in a path. When when a certain wheel is placed in the path of a cathode ray, it shows some mechanical effect. Means the wheels starts to move, rotate, right? It means that cathode ray produce mechanical effect, right? Second point. Third was that cathode ray consists of negatively charged particles known as electrons. Why negatively charged particles? Because you can see that the rays coming from the cathode, it is going towards the anode side, and we know that anode is positively charged, right? So that's why the cathode ray is negatively charged particles. Cathode ray is comprised of negatively charged particles, which are known as electrons. Cathode rays travel with a high speed, right? Travels with a high speed. Cathode ray can cause fluorescence. As you can see that we have used, the scientist has used the zinc sulfide light coating. So which is a fluorescent material. So cathode ray produces fluorescent. You can observe a bright color light when the cathode ray just strike that surface, that zinc sulfide surface. Okay. Sixth point was that cathode ray hit the object on which they fall due to transfer of kinetic energy of the object. Right? Cathode ray hit the object when it falls on any screen. So due to the transfer of kinetic energy of the object, the cathode ray hit that object. Right? Next is when cathode ray falls on solid, what happens? In solids, just like copper and any other material, X-rays are produced, right? So cathode ray produces X-rays also. Eighth point is cathode rays possess ionizing power, right? It has an ionizing power. Mean in the glass discharge tube, if there's a gas particles, this cathode ray when it strikes the gas particles, it ionizes that gas material, right? It ionizes that gas through which they pass, right? As you can see in the case of this, right? So here, this is a not fully evacuated. There are some gas particles in the discharge tube. So when this cathode ray strike that gas particle, for suppose here H2 is there, hydrogen gas is there, right? So when this cathode ray strike this hydrogen, it ionizes hydrogen. It ionizes particles, right? Okay, so cathode ray possesses ionizing power. Next is here they can penetrate through thin metallic sheets, Cathode ray can also penetrate through thin metallic sheets. The nature of these rays do not depend upon the nature of gas or the cathode material, right, or the electrode material which are used in discharge tube. Right, you can use any material. It doesn't depend on the nature of gas which is used in the discharge tube and the material of the electrodes also. Clear? So you can write down or you can take a screenshot of it. Just take the screenshot, then we will move forward. Then Neha,
Yes, ma'am.
okay. Okay, now here's the determination of charge to mass ratio of electron. Charge to mass ratio. So J.J. Thomson, for the first time, experimentally, he determined the charge to mass ratio. Who did the charge to mass ratio? Who determined? J.J. Thomson, right? So he subjected the beam of electrons released in the discharge tube as a cathode ray, right? And he influenced the electric and magnetic field. He do the same experiment which is being used over here in the cathode ray experiment, but in this case he applied some electric as well as magnetic field over here, right? When he apply electric and magnetic field, what he saw that these electrons, these when he applied this electric field, what happens, he just observed that there is some deflection over here, right? This cathode ray deflect towards the positively charged, right, positively charged electric field. And when he applied the magnetic field, what happens? It shows the deflection towards C. This is the C deflection, which shows the deflection when he applied the magnetic field, right? And A, this deflection shows when he applied the electric field. And this B shows when, see, what happens? Anyhow, he managed this. He just calculated some values over here, which determine later the charge to mass ratio. Like see, इन्होंने क्या किया, first he applied the electric field से क्या हुआ, he just saw some deflection over here. These cathode ray show some deflection towards positive charge, right? And when अब उन्होंने क्या किया, electrical field remove कर दिया, then he applied a magnetic field. Again he saw some deflection. Again the cathode ray is not traveling in the straight line. From here it bends towards C. It bends by some angle, by making some angle, and here you can see some deflection over here, right? So these were acting perpendicular to one another as well as the path followed by electrons. This is the path followed by electron, right? This A, B. So according to Thomson, what happens? The amount of deviation of particles from this path in the presence of electrical and magnetic field, these depends on some factors. Okay, we will see what are those factors. So anyhow, इन्होंने क्या किया? These इन्होंने electrical field as well as magnetic field ली and इन्होंने कुछ calculations किए. तो charge calculate किया, mass calculate किया, and after that he determined the charge to mass ratio for electron. Right. So let's see. This charge to mass ratio depends on which factors. Okay. So determination of charge to mass ratio is done by J.J. Thomson. Okay, let's see. You can take the screenshot of it. Okay. Now see, according to Thomson, what happens? The amount of deviation of the particles, see, the amount of deviation of the particles from their path in presence of electrical as well as magnetic field depends on these factors. Now, what are these factors? Now see, if the magnitude of charge of the particle is greater, if the charge is greater, then greater is the interaction with the electrical or magnetic field, right? Means the magnitude of charge is directly proportional to the deflection. if the magnitude of charge is more, right? See, if the magnitude of charge of the particle is more, then the interaction with the electric and magnetic field of that particle will be more, right? जितना ज्यादा मैग्नीट्यूड होगा चार्ज का उतने ज्यादा इंट्रैक्शन होगा इलेक्ट्रिकल और मैग्नेटिक फील्ड के साथ उस पार्टिकल का, राइट? एंड जितना ज्यादा इंट्रैक्शन होगा मैग्नेटिक और इलेक्ट्रिक फील्ड के साथ उतने ही ज्यादा डिफ्लेक्शन होगा, राइट? उतने ज्यादा एंगल के साथ वो डिफ्लेक्ट कर जाएगा. So just remember that. Greater the magnitude of the charge, greater the interaction between electrical and magnetic field, right? And greater will be the deflection. Clear?
Yes, ma'am.
Second factor was that mass of the particle. It depends on the deviation of particle, depends on the mass of particle. If the particle is lighter, particle means here I'm talking about the gas particle, right? If the gas particles in the discharge tube is lighter, okay, gas particles अगर light है, for example hydrogen है, तो hydrogen के case में सबसे ज्यादा deflection होते हैं, right? Because hydrogen is lighter particle. So if the gas particle is lighter, then greater will be the deflection, right? Means the mass of that gas particle is inversely proportional to deflection, right? Mass of gas particle is inversely proportional to deflection. If the mass is lighter, then the deflection will be more, and vice versa. Clear, Neha?
Yes, ma'am.
Third point was that the deflection of electrons from the original path increases with the increase in the voltage across the electrode, right? Means आप जितना voltage दोगे, जितना high voltage दोगे, then the deflection of electron will be high. Deflection will be greater. Okay, it increases with the increase in the voltage or a strength of the magnetic. If the strength of the magnetic field is greater, then the deflection will be greater, right? So these are some factors on which the deviation of particles depends, right? Yeah. So by this experiment, he just calculated a E by M ratio, which is charge to mass ratio. E over here is charge, magnitude of charge on the electron in coulomb, and M is the mass of electron in kg, right? E upon M ratio he just calculated, and it came to be 1.758820 into 10 to the power 11 coulomb per kg, right? This value you have to remember that. You should remember that. Clear?
Yes.
Okay, now see the charge on the electron. So the charge on the electron is given by R.S. Millikan derived, see, R.S. Millikan derived a method which is known as oil drop experiment, right? This is given in the NCRT in the box part. You can just read it. Okay, because ये आ नहीं रहे आपके एग्जाम्स में, तो just मैं बस overview दे रही हूँ. I'm not explaining it in details. Okay, because we have to complete this chapter by 23, before 23. So R.S. Millikan derived a method which is known as oil drop experiment to determine the charge on the electron, right? So he derived a oil drop experiment. By this experiment, he just calculated the electron charge on electron, which comes to be minus 1.6022 into 10 to the power minus 19 coulomb, right? And the mass of electron E upon M ratio means charge, magnitude of charge on electron divided by the charge to mass ratio, right? So 1.6022 into 10 power minus 19 coulomb divided by this. This is the charge to mass ratio, right? So because mass is always positive, that's why we are not taking the negative charge over here, right? So this comes to be the mass of electron is 9.1 into 10 power minus 31 kg, and the charge on electron is minus 1.6022 into 10 to the power minus 19 coulomb, right? You can simply remember these only minus 1.6 into 10 to the power minus 19 coulomb. So this was the charge of electron and the mass of electron, which was given by R.S. Millikan using oil drop experiment. Clear?
Yes, ma'am.
Okay, this was all about the cathode ray experiment. Next experiment was the anode ray experiment, right? Anode ray experiment. It was very much similar to that of cathode ray, and it was performed by E. Goldstein, Eugen Goldstein. Okay, तो Goldstein ने in 1886 में he performed this experiment to discover the proton. By using this, by this experiment, he discovered a proton, which is also known as positive particles. Okay, proton is also known as positive particles and also known as canal rays or anode ray. You can say anode ray. Okay. So yeah, just remember that anode ray were observed by E. Goldstein, but was named by Rutherford, right? E. Goldstein ने ये observe किया था, experimental data E. Goldstein ने दिया था, but he didn't name that ray. He just say the canal ray. Proper उन्होंने proton नहीं कहा था, right? He just say canal rays. So, but after Goldstein, Rutherford named this proton, right? Names a positive particle as a proton. Now let's see what he did in his experiment. Okay, so see, in 1886 he modified the discharge tube by using a perforated cathode. See, cathode ray experiment में जे थॉमसन ने क्या किया था उन्होंने एनोड को परफोरेट किया था, right? He just perforate the anode, but this time E. Goldstein perforated the cathode, right? Goldstein क्या किया था परफोरेट किया था कैथोड को. So and on reducing the pressure, what he did, he reduced more pressure and applied more voltage. So what he did, he observed a new type of luminous rays passing through the holes of perforations, and here he coated it with the zinc sulfide. Here he coated with the zinc sulfide material. Okay. So in that case, what he did, he just perforate this cathode, right, instead of anode. जे थॉमसन ने क्या किया था एनोड को परफोरेट किया था, but this time he just कैथोड को उन्होंने परफोरेट किए and उन्होंने क्या किया, इन्होंने रिड्यूस किया प्रेशर. He just reduced more pressure and apply more voltage, right? So he observed a new type of luminous rays coming from here, right? And passing through the holes of perforations. These rays passing through the holes of perforations, which is which is moving in the direction opposite to the canal cathode ray. Right? Cathode ray के केस में क्या हो रहा था? यहाँ से cathode ray से यहाँ towards anode particles move कर रहा था. But here in the case of this anode ray experiment, the rays are coming from the anode, right? Coming from the anode towards cathode. So these rays were named as positive rays or anode rays or as canal rays, right? So these rays are known as positive rays. Why? Because it was coming from the positive side and it was just attracting the negative terminal, negative electrode, right? Because we know that opposite attract each other. So this may be positively charged. That's why he just say Goldstein named it as a positive rays or an anode rays, right? Because it was coming from anode, right? And simply he just said it as a canal ray. Clear?
Yes,
It was just similar to that of cathode ray experiment. Now here, after doing this experiment, he just draw some properties of anode ray. He just observe some property. Again, anode ray travel in a straight line. Yeah, just one more thing. See, he observed that anode rays are not emitted from this anode, right? Anode ray is not emitted from this anode. It was emitted from a space between this and cathode, between these spaces, right? Means इसका मतलब क्या हुआ, ये एनोड in that case, just remember that cathode ray के केस में क्या हो रहा था, the rays were generated from the cathode, right? Cathode से वो generate हो रहा था, but here in this case the rays were not generated from the anode electrode, right? It was generated from the spaces between this anode and cathode, right? Means when the voltage, high voltage were applied, what will happen? यहाँ से कुछ rays निकल रही होगी and this will ionize हाइड्रोजन. यहाँ पे फॉर एग्जाम्पल इसमें हाइड्रोजन गैस फिल हो, राइट, फॉर एग्जाम्पल इसमें हाइड्रोजन गैस फिल है इस डिस्चार्ज ट्यूब में. सो दैट वो आयनाइज होगा और उससे कुछ पार्टिकल्स निकल रहे थे, मतलब हाइड्रोजन गैस से कुछ पार्टिकल्स निकल रहे थे, राइट. सो सिंपली we can say that these particles, positive particles, are coming from the hydrogen, right? They are coming from the hydrogen particles, hydrogen material, gas. It was not coming from the, well, it was not generating from the anode electrode. Okay, just remember the difference between these cathode ray experiment and anode ray experiment. Okay, so properties of anode ray. So what was the property? First property was same, that anode rays travel in a straight line, right? Anode ray travel in a straight line. But in the case, anode ray are positively charged. Yeah, anode ray are material particle. Yeah, just remember that. Anode ray depends on material. Anode ray depends on the nature of gas in the discharge tube, right? But cathode ray क्या कर रहा था? Cathode ray doesn't depend on the nature of the particle, gas particle, and the nature of electrodes. But here in this case, anode ray just are material particle. What does this mean? Material particle means it depends on nature of gas in the discharge tube. Okay. गोल्डस्टीन ने बहुत सारे एक्सपेरिमेंट्स किए, उसके बेसिस पे उन्होंने देखा कि मटेरियल पार्टिकल पे वो डिपेंड कर रहे हैं. उन्होंने डिफरेंट डिफरेंट मटेरियल यूज किया, नेचर ऑफ गैस, डिफरेंट डिफरेंट गैसेस पुट करके देखे डिस्चार्ज ट्यूब के अंदर, and he just concluded that anode ray are material particle because it depends on nature of gas in the discharge tube. Okay, and yeah, the charge to mass ratio of particles depends is found to depend on the gas from which these all originate, right? Charge to mass ratio of particles depends on the gas from which these all originate. Means it will be the charge to mass particles will of anode. The charge to mass particles of anode means your proton. It depends on gas particles. Means if the gas particles are changing, you will see the changes in the E upon M ratio also. Okay. So the behavior of these particles in the magnetic or electric field is opposite to that observed for electron or cathode ray. Right. So if when the Goldstein applies some magnetic or electric field, then he's observed that the anode particles behavior is just opposite to that of electron and cathode ray. राइट. कैथोड रे और कैथोड रे जैसे डिफ्लेक्ट कर रहा था, इट वाज जस्ट बिहेविंग ऑपोजिट टू दैट ऑफ कैथोड रे, राइट. सो दीज आर सम प्रॉपर्टीज ऑफ एनोड रे, you should remember that. Okay, now see, proton is the smallest and lightest. What is proton? So proton is the smallest and lightest positive ion which was obtained from hydrogen, right? It was obtained from hydrogen and was called proton, right? And mass of proton is 1.67 into 10 to the power minus 27 kg. And the charge on proton is plus 1.6 into 10 to the power minus 19 coulomb. Clear?
Yes.
Okay, let's see the discovery of neutrons. So it is a, what is neutron? So neutron is a neutral particle. But हमें कैसे पता चला कि neutron is a neutral particle? So it was discovered, and James Chadwick told us that neutron is a neutral particle, right? And who discovered the neutron? Neutron was discovered by James Chadwick in which year? 1932, right? Now see what he did. So he did some experiment. So he just bombarded uh, thin sheets of beryllium with fast moving alpha particles. Okay, so we will not see this in details. See first tell me if you have you take the screenshot of these. Anode ray experiment.
Yes, ma'am.
The properties of anode ray.
Yes, ma'am. Done, ma'am.
So now see what he did. He just in 1932, it was done by James Chadwick in 1932. So James Chadwick bombarded beryllium ion with the stream of alpha particles. See, beryllium is 4, atomic number is 4 and mass number is 9, right? And this is alpha particle. Alpha particle is helium. Helium particles are known as, this is alpha particles. Particles, atomic number 2 and mass number 4, right? So when he bombarded beryllium with a stream of alpha particles, he just noticed some radiations were produced, right? Some radiations were produced which are not affected by magnetic or electric field, right? He noticed that when he bombarded beryllium with a stream of alpha particles, right? When he bombarded alpha particles on beryllium, so what he observed? He observed that some radiations are coming over here, which are not affected by magnetic and electric field, right? And these radiations are consisted as a neutral particles because they are chargeless, right? तो उनके वो उसकी वजह से वो जो radiations जो आ रहे थे, they were not affected by magnetic or electric field because they were chargeless. If उनके पास charge होता तो they will be affected by magnetic as well as electric field, right? But these radiations were not affected by magnetic and electric field. So this James Chadwick, he just conclude that these radiations consisted of neutral particles, right? And he just named this neutral particle as neutrons, right? Neutrons. So you can see over here, beryllium से उन्होंने bombard किया alpha particles, right? तो क्या हुआ? Carbon. So when 2 plus 4, atomic number 2, and this is 4. So it will give you 6 atomic number. And here you can see the mass number should be 9 plus 4, 13, right? Mass number should be 13, but here carbon, ये हमें क्या मिला? Mass number 12. But so he just see that one mass is coming over here, right? One mass जो है वो loss हो रहा है, तो कहाँ जा रहा है ये? तो it is in the form of neutron. And 0. That's how we denote the neutron. Again, when he bombard the boron, right, with the alpha particles, he just observed it's nitrogen, right? Nitrogen 5 plus 2 is 7. But here 15 mass number should come, right? But here it is a loss of one neutron, right? So that's how he just observed that neutrons, there is some radiation which is unaffected by magnetic and electric field, and it must be a neutral particles, which further named as a neutrons. Okay, so that's how the discovery of neutrons occurred. Clear, Neha?
Yes.
This screenshot.
Yes, ma'am.
Let's see, the next is atomic model. Atomic model. आपने क्लास 9 में पढ़ा होगा atomic model. Thomson's model of atom, Rutherford model of atom.
Yes.
Yeah. So see, Thomson was the first model is Thomson model of atom. And he was the first one who proposed a detailed model of atom. Because see, discovery तो हो चुकी थी electrons, protons and neutrons की, but they don't know what where they are consisted. Means atoms में वो कहाँ कहाँ पे पाया जाता है, electrons कहाँ पे होता है, protons कहाँ पे होता है, and neutrons कहाँ पे होता है, right? Means proper detailed model of atom किसी ने अभी तक नहीं दिया था, right? First थॉमसन ने ये प्रपोज किया डिटेल्ड मॉडल ऑफ एटम, right? So Thomson was the first to propose a detailed model of atom. So what he did, so he just say that he just said proposed that atom may be regarded as a sphere. This is atom is regarded as a sphere, right? In which, see, he said that Thomson it consists of a uniform sphere of positive charge ion, positive charge in which electrons are present and at some places, right? And this model is also known as plum pudding model, or just like a watermelon model, watermelon model. Why watermelon model? Because see, the red part which we eat is the positively charged sphere, right? And the seeds of watermelon which are embedded in it, it is considered as an electron by Thomson, right? So basically, Thomson proposed that an atom consists of a uniform sphere, right? And this sphere is a positive. This sphere is positive, and the electrons are embedded in it, right? Just like a Christmas pudding. In the Christmas pudding, the what are these? These raisins are embedded in this Christmas pudding model, right? So this model is also considered as a plum pudding model. Now see, what are the limitations? So the limitations of this model was that this model was not able to explain the overall neutrality of the atom, right? Overall neutrality कोई explain नहीं कर पाया था this model, right? And this model is a static model, means it doesn't reflect the movement of electron, right? Movement of electron की इन्होंने कोई बात नहीं कही थी. It is a static model. Clear Neha?
Yes, ma'am.
Yeah. Further, scattering Rutherford scattering experiment has come. Yeah, this is the Rutherford scattering alpha scattering model, right? So in 1911, Rutherford performed some scattering experiment, right, in which he bombarded tin foils. See here, he just takes some radioactive elements, radioactive substances, which is covered in a lead box, right? And he performed some scattering experiment in which he bombarded tin foils. This here you can see that it is a thin foil of gold, right? Gold thin foil, right? Which is a, and this is a deflection screen, which is a fluorescent screen, which is made by zinc sulfide, ZNS, right? So what he did, he just bombarded particles, thin foil of metals like gold, silver, or platinum, right? And he can use also copper with a beam of fast moving alpha particles. Right here, the beam of fast moving alpha particles are coming over here. What happens? A thin gold foil, this thin gold foil has a circular fluorescent. Right, you can see over here, this is a circular fluorescent zinc sulfide screen around it. Right. So whenever this alpha particles struck this screen, a tiny flash of light was produced. Right. You can see the tiny flash over here. Tiny flash of light are produced over here. From this experiments, he made the following observation. Like, see, what are the observations over here? See, he's just observed that most of the alpha particles, means 98% of the alpha particles are passed through this foil without undergoing any deflection. Right? 98% means most of the alpha particles just pass through the foil without undergoing any deflection. Right? Any deflection, these are the most of the alpha. Right? Now, a few alpha particles underwent deflection through a small angles. You can see few alpha particles deflect over here by making some angles. Okay. Third observation of Rutherford was that very few were deflected back, making an angle of 180 degree. Right? They are deflected back. Now, from these observations, he just concluded he just gave some conclusions over here. Now, what are those conclusions? So he just said that he just conclude that because since most of the alpha particles pass through the foil without undergoing any reflection, right? So there must be a sufficient empty space within the atom. That's why most of the 98% of the alpha particles are undergoing without any deflection, right? So that's why we just said that there must be a sufficient empty space within the atom, right? Second conclusion was that because a small fraction of alpha particles was deflected, right? Very small fraction of alpha particles was deflected by small angles. So he just said that the positive charge has to be concentrated in a very small volume. Positive charge is enclosed or concentrated in a very small volume that is repelled and deflected a few positively charged alpha particles. Right? See here, you can see that in this, see in this second figure, in this second figure, figure number second. Okay, so these are some the incident beam of alpha particles, right? See, you can see over here some particles just repelled, just come across the this way, right? And most of the particles, alpha particles, are deflected, undergoing any with are passed through the foil without undergoing any deflection, right? Means 99%, 98%. Very small fraction of alpha particles was deflected by small angles, right? These are small angles, ये small angles बना के ये deflect हो जा रहे थे, right? और जो उन्होंने ये क्या किया, उन्होंने ये conclusion draw किया accordingly that a positive charge has to be concentrated in a very small portion, in a very small volume, right? And this very small volume was of atom was called the nucleus, right? Rutherford said that it is a nucleus, which is concentrated in a very small volume, right? And the volume of nucleus is very small as compared to total volume of atom. He said that volume of nucleus is very small as compared to total volume of atom. Okay, the nucleus is surrounded by electrons that move around the nucleus in a very high speed in a circular path called orbit, right? He just said in his nuclear model of atom, Rutherford nuclear model of atom, he said that the nucleus is surrounded by electrons. Nucleus is surrounded by electrons that move like this. Nucleus is surrounded by electrons like this, and it's moving in a orbit, circular path called orbit in a very high speed. Okay, he said that. And the last conclusion was that electrons and nucleus are held together by electrostatic force of attraction. He said that in between the electrons and nucleus, there is a force acting between these two, which is known as electrostatic force of attraction. Right? Now see, what are the drawbacks of Rutherford model? What are the limitations? Okay, okay. So he said that, what he said that? He said that nucleus is surrounded by electrons, right? That move around the nucleus in a very high speed in a circular path. But when a body is moving in an orbit, we know that it achieves some acceleration, right? Because if आपने फिजिक्स से पढ़ा होगा कि जब कोई भी बॉडी मूव कर रही होती है ऑर्बिट में तो it will achieve some acceleration, right? And if it is achieving some acceleration, so an electron is moving around the nucleus in an orbit is under acceleration. It's under acceleration. So according to Maxwell's, we know that according to Maxwell's electromagnetic theory, right? What he said in his theory, charged particles when accelerated must emit electromagnetic radiations. When a charged particle is in acceleration, they must they must emit some electromagnetic radiation, right? So therefore, in this case, an electron in an orbit will emit radiation because it's moving along its orbit, right? According to the Rutherford, electron is moving along a circular path orbit. So it must be accelerating, right? It must be accelerating, and according to Maxwell's electromagnetic theory, if a particle is in acceleration, it must emit some electromagnetic radiation, right? So electron in an orbit will emit radiation. This will emit radiations, and the energy carried by these radiations comes from electronic motion, right? यहाँ ये radiation से जो energy आ रहा है, it will create some electronic motion, राइट? सो जब ये इलेक्ट्रॉनिक मोशन क्रिएट करेगा तो ये क्या होगा, ये मूव करते 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 ये क्या होगा, दिस विल गोज इनटू द न्यूक्लियस, दिस विल गोज क्लोज टू द न्यूक्लियस, राइट? सो but actually this doesn't happen, right? But actually it doesn't happen. So it will further जब Bohr's model आया, then he proved that Bohr's this is the drawback of Rutherford, right? He said that nucleus is surrounded by electrons that move along the nucleus in a very high speed in a circular path, right? But it is wrong. But it is wrong because if a according to Maxwell's electromagnetic theory, if a charged particles is in acceleration, they exhibit some electromagnetic radiations, right? And electrons अगर electromagnetic radiations carry करता है तो energy जो आ रही है radiation से, right, from the electronic motion, तो क्या होगा, this electrons, ये electrons क्या करेगा, मूव करते 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 it will goes into the nucleus, right? But actually it doesn't happen. So Rutherford model cannot explain the stability of atom, right? Rutherford model, it doesn't explain the stability of atom if the motion of electron is described on the basis of classical mechanics, right? Classical mechanics and Maxwell's electromagnetic theory. ये इलेक्ट्रोमैग्नेटिक मैक्सवेल्स के इलेक्ट्रोमैग्नेटिक थ्योरी को फुलफिल नहीं कर रही थी, राइट? दैट्स व्हाई ये रदरफोर्ड मॉडल का सबसे बड़ा ड्रॉबैक था. क्लियर नेहा?
Yes.
Okay, so write down Rutherford model cannot explain the stability atom if the motion of electrons is described on the basis of classical mechanics and Maxwell's electromagnetic theory. Okay. Second drawback of Rutherford was that रदरफोर्ड ने उन्होंने कोई आइडिया नहीं दिया था कि इलेक्ट्रॉन्स का डिस्ट्रीब्यूशन कैसे होता है अराउंड द न्यूक्लियस, ओके, अकॉर्डिंग टू देयर एनर्जीज. सो रदरफोर्ड model does not give any idea about distribution of electrons around the nucleus and about their energies. He didn't give any idea about the distribution of electrons, right, and about the energy of electrons in different levels. Written?
Yes, ma'am.
Atomic number and mass number. Okay, so first we will talk about the atomic number. Okay, so atomic number, it is denoted by capital Z, right? Capital Z, Z. So atomic number, you know very well, it is equal to the number of protons present in the nucleus of the atom, right? Of that element. So write it down. It is always equal to number of protons present in the nucleus of the atom of the element. And yeah, it also represents the number of electrons also. Number of electrons is equals to the number of proton. Okay, for example, if the potassium, for example, okay, what is the potassium atomic number? Neha?
19.
Yes. Right. So if the atomic number of potassium is 19, so what does this mean? So it means that it has 19 protons, right? Number of proton is 19, right? And so as the number of electron is also 19, right? So the number of proton in potassium is 19 because its atomic number is 19, right? So means Z is equals to 19. Right, Z means atomic number. Atomic number is 19, so the number of proton is also 19, and the number of electron is also 19. Right. Now see, second is the mass number, which is denoted by capital A. Right. So the neutrons and protons present in nucleus of an atom are collectively known as what? Nucleons. right? Neutrons plus protons are collectively known as nucleons. For example, X, X is in some element, right? So here we will write the atomic number, which is Z, and here on the superscript, in the subscript, we write the atomic number, and on the superscript, we write the atomic mass. No, sorry, this is the atomic number over here, and this is the atomic mass over here. This is the atomic mass A, and the atomic number here is Z, right? For example, for carbon, right? So carbon atomic number is 6 and the mass number is 12. So we will write like this. Written.
Done, ma'am.
And see the mass number, which is A, is equals to the number of protons plus the number of neutrons. Number of protons and the number of neutrons, right? Which is P plus which is N. For example, if the mass number is given, and so we know the protons, number of protons, so we can calculate the number of neutrons from that. For example, if the if I give you oxygen, right? Calculate the number of neutrons, neutrons in oxygen atom, right? So how you will calculate? So we know that oxygen atomic number is, what is the atomic number of oxygen?
8.
Yes, 8, and atomic mass is 16, right? So we know that atomic number के equal होता है number of protons, right? Atomic number के equal क्या होता है number of protons. So the number of proton is 8, right? And what is the mass number? Mass number, which is A, A is equals to 16. So we can calculate the number of neutrons. Number of neutrons, N is equals to A minus P. A 16 minus 8. So 8. So what will be the number of neutrons? So number of neutron is 8. Number of neutron is 8 and the number of electron and proton is also 8. Clear?
Yes, ma'am. Done.
So remember this formula. Remember this formula. Mass number A is equals to P plus N. Right. Next is your isotopes. What are isotopes? So what are isotopes? What are isotopes, Neha? Identical atomic number but different mass number.
Yeah.
Right.
Yeah.
Mass number is different but atomic number is same. Write down. Right. For example, isotopes of hydrogen. So, for example, like this is H1 1. This is hydrogen, which is denoted by capital H. H1, when the atomic number is 1, atomic number will be same, but atomic mass will be changes. Right? H1 2, which is, what is this? This is deuterium, which is denoted by capital D. This is deuterium, isotope of hydrogen. And H13, if the mass number of hydrogen is 3, then it is known as tritium, which is denoted by capital T. Deuterium, this is hydrogen. Hydrogen, or simply you can call it as a protium. What is this? Protium. This is deuterium. And this is tritium. So these are the isotopes of hydrogen, right? Means here you can see that the mass number, what is the mass number of these three? Mass number is different. Here in the case of C, the mass number is 1. So A is 1. And what is the Z? Z is also 1. So in this case, A is 2, right? But Z is 1 because the atomic number will be same. Here you can see that the mass number is 3, but the atomic number is same, right? Means, what does this mean? Means in all the cases, the number of protons are same. In isotopes, the number of protons are same. Means here in this case, in the case of isotope of hydrogen, the number of protons is 1, right? If the number of protons, we know that, so we can calculate the number of neutrons they have. So can you tell me what are the number of neutrons in this high protium, deuterium, and tritium?
Uh, will
Yes,
be
for hydrogen. For protium,
so
what
that
will be
one
the
it will
neutron?
be 0, right? Because 1 minus 1. So
0. Yeah, it's 0. For protium, it is 0. Number of neutron is 0.
1,
For deuterium, it is 1. For
1,
tritium, it
and
is
it's 2.
2. Right, very good. So this will be the structure. Means one electron will be there and only one proton is there. For the protium, right? This is for protium. And one electron, electron is there, and one electron and one proton is fixed in all these three, right? And this is for deuterium. This is the atomic structure of deuterium, right? Means one proton and one neutron. And in the case of tritium, one electron is there, one proton is there, but two neutrons are there, right? So this is the case of tritium. Now, I hope it is clear now. What are the isotopes,
Yes, no.
right? Similarly, you can see the isotope of chlorine. Chlorine exists as a has two isotopes. Chlorine has two isotopes. Chlorine 35 and 37. Yeah, these are the two isotopes of chlorine. So in this case also you can see the atomic number is 17, but the atomic mass is different, 35 and 37. Means the number of electron and protons are 17, right? But the number of neutron is different. Number of neutron is 35 minus 17, which is 18. 18 in the case of 35 and 20 in the case of 37. Right, clear? Now you can find the number of electron, protons, and neutrons in each and every isotopes. Right? And yeah, carbon exists. Carbon exists in three isotopic form: C6, C12, C13, and C14. Right? Yeah, nitrogen also. Nitrogen existent, nitrogen 14 and nitrogen 15. So these are some isotopes of some elements. Okay. Oxygen also exists in oxygen 16, 17, 18, right? Sulfur 37, 33, 34, 36, and there are more examples of isotopes. So these are some examples you should know about this. Clear, Neha? Any problem with this?
No, ma'am.
Okay. Now let's see what are isobars. So what are isobars, Neha? Just opposite to that of isotope.
Same atomic number, but different atomic.
Yes. Atomic number. No. Atomic mass is same. Atomic isobar it is. Right? आपने तो आइसोटोप का ही डेफिनेशन बोल दिया. Isobar means atomic number is different. Atomic number is different, but atomic mass is same. But mass number is same. Clear? So this is the isobar. Now let's see what are some examples. Examples can be carbon 14 and nitrogen 14. Right? So these are two isobars. So you can see that the mass number is 14 in both of these, right? Mass number is 14, right? But the atomic number is different, 6 and 7. Clear? So these are some isobars. So in the case of isobar, we can say that the number of protons and electrons is different. Number of electrons and protons is different. Clear? So in these case, what are the number of? So you can see that number of electron here is 6 in the case of carbon, but here number of electron is 7, right? Number of electron in the case I'm talking about the carbon, it is 6. And the proton is also 6. Number of proton is also 6. So number of neutron will be 14, mass number minus 6, right? Right. So, and in the case of nitrogen, you can see the number of electron 7, number of proton is again 7, but the number of neutron is 14 minus 7, right? Means 7. Means in the isobar case, the number of electron and number of proton and number of neutron is different of both for both the isobars. Like here you can see the number of carbon in the carbon and nitrogen, the number of electron and proton is different. Here in the carbon it is 6, but here in it is 7, right? And the number of neutron is also different, 8 and 7. Here, another example you can take. Sorry, second example. Argon 40, potassium 40, and carbon. Yeah. These three are the isobars. Why isobars? Because you can see over here, mass number is same, 40, 40, 40 for argon, potassium, and calcium, but the atomic number is different, right? So atomic number and mass number is different. Mass number is same, and the atomic number is different. So the number of electron and proton will be different, right? And the neutron is also different for both of all these three, right? So these are some examples of isobar. You should remember that. Yeah, one more thing, नेहा, जो आपने फर्स्ट यूनिट में आपने ये नहीं पढ़ा था, atomic average atomic weight, how to calculate the atomic average atomic weight. Like if isotopes, for isotopes, atomic number is same, but the mass number is different, right? So in this case, how to calculate the atomic weight, right? How to calculate the atomic weight. So here is a formula for calculating the average weight. So average weight is if two isotopes are given, right? Or if more than two isotopes are given. So what you have to do, just AW, I'm writing the atomic weight of first into the relative abundance, right? Into the its relative abundance. Now, what is its relative abundance? Means a percentage of occurrence in nature, right? What is the percentage? Relative abundance is the naturally occurring percentage, right? So relative abundance of first plus the average weight of second isotope into its relative abundance, right? Plus the third, right? And so on, right? जितने भी आपके isotopes दे रखे होंगे, you have to just multiply the atomic weight into its relative abundance and just sum up कर देना आपको, add up कर देना, right? So here in the case of chlorine, I'm taking the examples of chlorine over here, right? So chlorine यहाँ पे दो isotopes है chlorine के. So we will take AW1 atomic weight of first into its relative abundance plus atomic weight of second into its relative abundance divided by the sum of their relative abundance Ra1 plus Ra2, right? So this is the formula of average weight to calculate the average weight of isotopes. Okay, it's given, some questions are given in the NCRT. First chapter, you can see. Like here, they have given the isotopes of argon, right? Argon दे रखा है, उसके relative abundance दे रखे हैं. You don't have to do something. You just have to put the formula. Just remember this formula for average atomic weight. This is for average atomic weight, right? And just substitute the value and you will get the answer. It's very simple.
And
Okay. Yeah, see, here's another term which is known as isotones. Isotones. Isotopes we have seen, isobars, and the third one is isotones, right? So what is isotones? So atoms of different element which have the same number of neutrons, right? Atoms of different element which have same number of neutrons, means the number of neutrons is same, right? For example, potassium K19, right, and 39, and calcium 20, and its atomic weight is 5. So if you just calculate the number of neutrons, you will find that the number of neutrons for both these are same, right? Means that these two are isotones with each other, right? These two are isotones. Just calculate the number of neutrons, Neha, and tell me. Second example is carbon 14 and oxygen 16. These are also isotones. Okay. Have you calculated the number of neutrons?
20,
Yes. For both these?
20, yeah.
Yeah. So you can see that these are the atoms of different elements, right? This is potassium, this is calcium, but they have the same number of neutrons, right? Means they are isotones. They are isotones with each other. Okay. If someone asks you, give some example of isotones, so you can give that example. Again, there is another example of isotone, which is carbon 14 and oxygen 16. So in this case also, you can find the number of neutrons, which is 14 minus 6, right? Which
Eight.
is 8. And here also 16 minus 8 means 8, right? So you can see that here also the number of neutron is same, means they are isotones. Clear?
Yes, ma'am.
Okay, there's another term which is known as isosteres. 5 minutes are left, so we will do some definition. I'm not going to start the new topic. In the next class, we will try to cover the means from the Bohr at atomic model. Yeah. The next one is your isosteres. Isosteres. So what is isosteres? So the molecules which have the same number of atoms and electrons. Number of atoms and electrons are same. That means they are isosteres. We will talk about the molecules here, right? हम अभी तक क्या बात करें एलिमेंट की बात कर रहे थे but here in isosteres we will talk about the molecules which have the same number of atoms and electrons. These are known as isosteres. For example, carbon dioxide and N2O, right, nitrous oxide. So let's find the total number of atoms. Total atoms, how many atoms are there? So for carbon, carbon 1 carbon is present and 2 oxygen, so 3 atoms, right? And in this also 2 nitrogen and 1 oxygen. So here also total number of atoms is 3, right? Now find the number of electron, number of electron, number of electrons. So in carbon, carbon is 6. Atomic number of carbon is 6, right? So 6, number of electron will be 6 in carbon plus the oxygen atomic number is 8, right? The number of electron will be 8 in oxygen. 8, but here 2 oxygens are there. So 2. So 6 plus 8 to the 16. So it will give you 22 electrons. 22 electrons, right? Similarly, you can find here also for N2O, the number of electrons here will be for N2, for nitrogen, 7. For 1 nitrogen, 7 number of electron into 2 because there are 2 nitrogen plus 8. 14 plus 8, so you will get 22 electrons. So here you can see that these two molecules have same number of atoms as well as same number of electrons. So we can say that these two molecules like carbon dioxide and N2O, nitrous oxide, is isosteres. Isosteres with each other. Clear, Neha?
Yes, ma'am.
Okay, so that's all for today. Isosteres, we have done this. Okay, in the next class, we will start the Bohr atomic model. And if possible, if the syllabus अगर हम नहीं complete कर पाए, तो we will plan extra class for you. We will schedule an extra class. Okay.
Okay.
If from today's class is there any doubt, please ask. Puche.
No, ma'am.
Everything is clear?
Yes.
Okay, Neha. So that's all for today. See you in the next class. Okay, please
Thank you.
revise this concept.
Okay.
And all the very best for your exam. Just prepare well. And if there is any doubt in any topic, you can ask me in the next class.